Here's lab number 4, magnetic braking. We examine a magnet as it falls through an aluminum foil tube. The purpose of this lab is to examine how Faraday's law can explain magnetic braking and model magnetic braking and compare it to experimental observations. The results was that our time in the tube model was 0.411 seconds, and the time observed experimentally was 0.365 seconds. Now, our fundamental physics principles is Faraday's law, which states that the rate of change of magnetic flux through a surface is the um, path integral of electric field around the surface. Newton's second and third laws, magnetic force on a current and magnetic dipole field. Our system is a bar magnet. We examine the force of gravity and the force of magnetic force on the bar magnet. Surroundings are the foil tube, everything else. Initial conditions, the magnet has zero velocity. Assumptions, bar magnet is a magnetic dipole. Only forces acting on the magnet are gravity and magnetic force, and this is our value for the resistivity of aluminum foil. Here is our observed data. This is our time for the falling magnet, and we average it to 0.365 seconds. And here is our magnet and tube geometry. Here is a video of one of our trials.
This is trial 2. Go.
Here's our code. This section describes a calculation of magnetic flux, or the change in magnetic flux through one simulated ring of the entire tube. And then these are some other equations we use to find our final force. F on one ring is this value, which we simulate somewhere. Um, current through the ring is EMF over resistivity. This part, the sine theta, I kept getting the wrong sign. So from definition of the cross product, it's just B hat, the x component. And then, of course, Newton's third law, this is how I find the force on a magnet is from the calculated force on it's the negative force on the ring. And here are our results. What does the shape of the velocity versus time plot tell you about the force acting on the bar magnet? Well, the whole time, gravity is stronger than the magnetic force because it never gained a constant acceleration. But you can see that it begins to approach a terminal velocity as it moves through the bar. So I think that if the bar were, or the tube were a little longer, it may have reached a terminal velocity. But then, of course, gravity would take over once again. Now, assume you're looking from above. Since the south pole is moving down first towards the magnet, um, as a magnet moves toward a ring, the magnetic field is increasing upwards, and therefore negative d, this should be flux, over dt points down, and by Lenz's rule, current goes counterclockwise, or clockwise, sorry. Current would go clockwise. Therefore, red is clockwise, and as it moves away from a ring, that would mean the current is increasing downwards. So then negative change in flux would be going upwards, so blue is counterclockwise. And if the magnets were flipped, motion would not change. Currents would flow in the opposite directions, but it would still have the same dB dt. So magnetic force always opposes motion. And flux is dependent on velocity, and because the geometry is the same. Experimental time is shorter than the model time, and this could be due to experimental error with inaccuracy in the time measurements, or we could have assumed the wrong resistivity, or and also the bar magnet it could also just not be an ideal dipole. It's made up of many atomic dipoles, so that might make a more accurate model. Now, what if the resistivity of the conductor were reduced as close as possible to zero? How the dynamics of the falling magnet change? Well, the current would run in such a way that the net change in flux is near zero, like a superconductor. And of course, the current would be higher with less resistance, so it would experience stronger braking and reach terminal velocity faster than with more resistance. What if holes or slots were cut into the tube? Well, then their current could not flow easily through the tube, so it would have a lot more resistance through certain sections if there were holes. So the magnet would fall faster because current could not flow through segments of the tube with holes. And F equals I times 2 pi r b m sine theta. Um, was radius, not resistivity. So with less I, there would be less upward force. And that is all.